Okay. Oops, sorry. So as we work these problems, kind of keep all this in mind. So drawing pictures, optional. Doodling, including like writing in equations that you think you can, that'll help you, optional. Taking the numbers with the units and just kind of putting them on your clear piece of paper, optional, but it's helpful sometimes. Two things that are not optional is always include units like seconds or meters or miles. Always include units, and always show all of your work. So, all right. So we're going to piggyback on the question that we left off on Friday. Okay, we had this car. We were given the amount of time it took, 4 seconds to go, let's see, what, 80 meters? Okay, so we came up with velocity or a speed. We'll talk about what's the difference between speed and velocity, because there is a difference. But we came up with a speed, an average speed of this, like you guys did in your homework, by taking 80 meters divided by 4 seconds. 20 meters per second. Cool. So now this is question number 6 that you did. Actually, in a minute, I'm going to assign question number 5, which is kind of like 6. So good job, guys. Now here's the deal. Now we have a different problem, and it says, how far in meters does the car travel in 2.5 seconds at this speed? Let me go ahead and make that a little better problem for you. For instance, you guys do this all the time in your head, okay? You are driving 60 miles per hour. All right? Driving your car, 60 miles per hour. You are going to go somewhere that is 30 miles away. How long is it going to take you to get there? It's going to take you about 30 minutes. If you're driving, if you can go, I think we're on the same page, Devin. If you can go 60 miles in 1 hour, right? 60 miles in 1 hour. That's how fast you're going. That's like a property of your car. Okay. To go 30 miles, how long will it take you? A half an hour or 30 minutes. Does that make sense? Okay. That's kind of, oops, sorry. 3 minutes. How's that? That's better, right? That's kind of what this problem is. But let me go ahead and show you how I would work this problem. Okay, so your question was, how long will it take you to get 30 miles down the road? So here's how I would work this problem. Not the problem that is in your notes, but this 60 miles per hour problem. What I would do is I would write the term 30 miles, and I would put it over 1, and then I would recognize that how fast you're going. Okay, in 1 hour, you're going 60 miles. Now, what I just did here in orange, this is supposed to be orange, working the problem, this is how long, oh, darn it, that is how far you're going to go, okay, and this is kind of the property of the car. What I did here in orange, okay, is kind of what we call the factor label approach of working this problem. Okay. So let's erase all of this, and kind of with that in mind, let's look at the real problem. I think I can erase by doing this. So remember, one of the things that is optional is to, part of doodling, is to go ahead and pull out information from the problem and write it on your clean piece of paper. Sorry about all those little dots. We're just going to go with that. Okay. So here we go. How far in meters? So I'm going to put question mark meters. That's kind of what I do. How far in meters? Now we're really doing the problem. How far in meters does the car travel in, I'm going to put T for time, is equal to 2.5 seconds. The last little bit of information is this, it's going at the speed in the bullet above it. It's going 20 meters per second. Okay, so the last thing I'm going to doodle is I'm going to say speed is equal to 20 m for meters over 1 second. 20 meters for 1 second. Okay, so those are kind of three things that I have going for this particular problem. So do you see where if I'm after meters, actually I can take this first term, t, okay, I'm going to take that time, 2.5 seconds, and I'm going to put it over 1, 2.5 seconds over 1, okay, and I am going to go ahead and then, if I want seconds to cancel, I can go ahead and insert my speed as my second term. 20 meters per 1 second. Okay? And I know my 5 and my s kind of look similar here, 2.5 s per seconds. But do you see where one of the things you might have learned in algebra is that if you have the same thing in the top and the bottom, like the numerator and the denominator, what can you do with them? You can cancel them. Exactly. And so actually, that is what I am going to do. My units, not any numbers, but my units of seconds will cancel. Okay, so I have just set it up using what we call kind of a factor. The factor part is actually for your seconds canceling. Factor label, and the label part is that the label means the units, so factor label method. So now on my calculator, if we take 2.5 times 20, what do you get? Thank you, you get 50. The other thing about this sort of approach is that the units that are in your problem are going to be the units that go with your answer. So we have units of meters here, and so that means units of meters there. Okay? So now you don't have to work it this way, but it's helpful, I think. However you work it, you need to show what you plug into your calculator. As I was working this, I had a recollection. This is how I work this problem. But I started kind of having memories of, how does this go? V is equal to d over t, right? Distance over time. Okay, and you can kind of rearrange that. So in this case, if we're after distance, that's velocity times time. So you can do that too. Does that make sense? I'm fine with that. Why I say rearrange, this same relationship, d is equal to v times t. So I'm good with either of that. Okay? All right. Clear as mud. Okay. So let's do another one. But it's a little bit different. And again, you can use the, if you want to, let's go straight to the d, or let's go straight to the, this relationship. What did we say? V for velocity is equal to d divided by time. Okay. In this case, how long will it take in seconds? So actually, we're after t. How long will it take? Now, I don't teach algebra, which might be a good thing. But let me go ahead and tell you, if I knew that what I wanted to solve for in this case was how long does it take t, what I would do is it's called kind of crisscross. Okay, I would flatten it out, and I would say v times t is equal to d. That's how I would start. That's exactly what we used in the previous relationship. Then I would say if I want t all by itself, okay, what I am going to do is divide both sides by v. Okay, so the one I can use here if I want to is simply, let's see, now v divided by v. Okay, these go away, right? V divided by v goes away. and we have t is equal to d divided by v. So t is equal to d divided by v. So we could work this problem. Okay, I'll kind of show you how you could work this problem. So all you just need to do is take the distance, 136 meters, and divide it by the velocity, which is 20 meters per second. I'll do it that way, and then I'll do it the other way, how I would do it. Okay, so using this relationship, t is equal to this approach, 136 meters divided by 20 meters per second. Okay, let's see, is that 68? I think so. Your calculator will say 68, right? Or, what will your calculator display? Thank you. That didn't sound right. 6.8. That's better. Cool. 6.8. Okay, oops. 6.8, and units would be actually seconds because it's time. Now, you can do it that way, and I would tell you the way, that which is perfect, and I'll tell you the way I would do it looks like this. Let's put it in purple. Working the same problem, what I would do is take the 136 meters and put it over 1. Okay, and then when I did that, I would use the 20, unpack the 20 meters per second like I did before, 20 meters per 1 second. That's how fast you're going. And I would recognize that this speed, if I want meters to cancel with meters, I'm going to have to flip this. So actually, this I'm going to have to flip. When I say this, I mean the speed I'm going to have to flip. The reason is because I want 20 meters on the bottom, 1 second on the top. That's how I would do it factor label. And then meters cancel, and we're left with units of seconds, and it's the same problem. Are there any questions about that?
So I couldn't do it either one of those ways, really.
Okay.
But on like a test, when we're showing our work, like we won't get talked if we're doing it a different way.
Did you write it down? Let's see.
Yeah, like I did like the cross multiplication that we were taught in nursing.
Okay. Thanks for pointing that out.
And I still got the same answer, but
right.
It's not the same.
That looks, yeah, that looks good. You're showing me your work, and that looks good.
Okay.
I agree. Perfect. Okay? Yay. Okay, so let's do another one. And however you're going to do it, can meet you on the other side. Or actually, this one's pretty straightforward. This one isn't using speed and time to get distance, or using speed and distance to get time. This first one is, based upon this information, what is the speed of light? Based upon this information, what is the speed of light? So basically, we have a little bit of light, a little photon piece of energy coming from the sun. Okay, they show how far that light needs to go in the top number. Okay, this is how far it needs to go from the sun to the earth, and this is how long it takes. Okay, so we have distance and time, and we're supposed to come up with a speed. That's not too bad. That's kind of like what you guys did for your homework. So we'd say speed, what, is equal to distance, which is 1.50 times 10 to the 8th. You guys are going to get some work using scientific notation. 1.50 times 10 to the 8th kilometers divided by the time. And it looks like they want units of kilometers per second. So we're going to go with this 500 seconds. Okay. So We got to remember what we talked about, scientific notation. So for scientific notation, the 1.50 times 10 to the 8th, you're going to put 1.50, it's the coefficient. You're going to find your EE key, and you're going to put 8. And then you're going to simply say divided by 500. I got to count zeros here. I got a 3 with 5 zeros after it. Did you guys get that too? Actually, it's a classic speed. So let's see, let's go ahead just for kicks and pack that up. If we were going to pack that up, the decimal is right here after the 0. So we need to move it over 1, 2, 3, 4, 5 places. So packed up in scientific notation, that is 3. We'll go ahead and say 3.00. Or it could be 3, times 10 to the 5th kilometer per second. Any questions about that? So that's that one. Motion is definitely, motion, or speed is definitely an important aspect of motion. Okay, so we're going to use that now. Okay, and we're going to use the fact that light travels, I'll go ahead and remind us what that was. From the first problem you have in your notes, speed of light is 3, we'll just go ahead and keep it packed up, 3 times 10 to the 5th kilometers per second. So now in this one, we're supposed to use that to our benefit and say, all right, let's say light or any sort of energy like light leaves Mars. How long does it take to get to Earth? And they go ahead and they give us the distance. So I'm going to go ahead and show you how I would do this factor label. I would pull out, this is my distance. Okay, my distance is what is that? 225,300,000 kilometers. And I would make that my first term, put it over 1. $225,300,000 kilometers over 1. And then I would recognize that I want my kilometers to cancel and I want to be left with seconds. So I would probably go back up here and doodle my speed, and I would say that what that really means is 3.3 times 10 to the 5th kilometers per 1 second. And then with that in mind, I would say, all right, I'm going to use that to my advantage, but I want kilometers to cancel, so I'm going to flip that. So flipped, it looks like this. In 1 second, I'll put that in the top, it travels 3 times 10 to the 5th kilometers. And when I do that, now my kilometers cancel. Okay, and we're left with units of seconds, which is exactly what we wanted. What do you think? Or you can use the V is equal to D over T and solve for T. So, good thing, all right, so 225,300,000 divided by, I'll just put 300,000. I got 751. Is that what you got? Okay. And units would be seconds. how would you convert, awesome, so that's how much time it takes for light to get to us from Mars. How would you convert seconds into minutes? Just curious. 60. 60 seconds per minute, exactly. So actually, I'm kind of running out of room. I'm going to kind of put it up there at the top there. What I would do is I would actually, like you were saying, 60 seconds equals 1 minute. In other words, there's 1 minute per 60 seconds. I don't know if you guys can see that. 1 minute per 60 seconds. And then actually, I would go ahead and work the problem like this. I would put 751 seconds over 1. Okay. And do you see where if I go ahead and plop in the 1 minute over 60 seconds, my seconds cancel, and I'm left with units of minutes? So 751 divided by 60, I got 12.516666, looks like repeating. So how should I round this? What do you think? 12.2. I like it. 12.5.
Since there's 2 decimal places, should it be like the very beginning of the problem, there's 2 decimal places.
Ah, the very beginning of the problem.
Like when you rounded, you took the 0 off of the 3.
Yeah, I think we're allowed. We're limited by. I think we're allowed 3 digits. I think what you're saying, I should only like have 1 decimal. I should only have 1 decimal because that's all I carried over.
Well, Friday you said something about we're supposed to use the smallest amount of decimal places.
The smallest amount of decimal places.
Or the largest amount when we were rounding them.
I think though, and this is kind of, the thing is the smallest amount, how do I say this?
I think it was the largest amount. That's what you said in here when we rounded these parts.
Use the smallest, yeah.
And then you gotta have the amount here.
Right. The thing is, like the relationship between minutes and seconds, that's what we say exact, and so that doesn't drive anything. So, and if with that in mind, the 751, we've got 3. So that's actually why we go with 3 for our time. So, but if you went with 1, that would be fine. If you went with 2, that'd be fine. If you went with 3, that would be fine. And don't give me 10 billion digits. But that's why that works that way. Good. Are there any questions about this? How are we doing? Okay. So kind of like I mentioned, what I'd like to do is the 6 that you guys sweat through or whatever, I want you to go ahead and do 5. Now the thing about number 5, question 5 on page 49 is the answer's in the back of your book. Or not in the back of your book, the answer is in the front of the book. It's right in green. But go ahead and work that one and turn it in. I'm pretty sure the way, if you choose to do the online part, you don't have to do both. If you choose to do the online part, I think you get sort of different numbers. I think is what they kind of randomize the numbers. Any questions? Okay. And 6, if you want to take another try at 6, and now that we talked a little bit, you can, and hand that in. That'd be cool. Or if you just want to leave your 6 the way it is, and I won't penalize you because we didn't talk about 6, that's fine. So but 5 is very similar. Okay? All right, now I also wanted to get to this sort of problem. There's one other type of problem I want to get to today. Okay. Now, we've been talking about speed, and speed is quick and dirty distance divided by time. Okay, speed is distance divided by time. Now, there is a subtle difference between speed and velocity. You kind of need to, if you're dabbling in physics like we are, we need to kind of know the difference between velocity. Velocity takes it up a notch. Okay, velocity is not just how fast you're going, but the direction that you're moving. Okay, and in physics, that's definitely a player. So velocity, like I said, kind of adds direction to how fast you're moving. Okay, so for instance, we have a couple of examples here. A car that is tootling down the road. You could say its speed is 45 miles per hour. If you wanted to say something, if you wanted to complete that thought with its velocity, you'd also have to give speed. So we could say it's going 45 miles per hour toward the northwest. Okay? Northeast, excuse me. So we have given the direction. So now that's a velocity. So what works real well for velocity is using these vectors. I think I mentioned the other day, these are called vectors. Vectors. V-E-C-T-O-R-S. Okay? So we looked at vectors the other day with forces. If it's a short vector, okay, it's a small force. Okay, so these are different velocities. So A is going faster than B, right? Left, right, A and B. But they're both going in the same direction. This would be another velocity. Okay, again, the length kind of gives you the speed or the magnitude of motion, and the direction of the arrow tells you the direction it's moving. This is another sort of important motion, right? This is like a kind of a circular motion, okay? So velocity kind of ups speed by giving direction to. Now, there's another important thing in physics called acceleration, and we're all kind of familiar with it. Heck, our cars, when you push the gas, that's called the accelerator, right? Hit the accelerator, dude, Sometimes you're driving down the road and you're behind somebody going slow, you're like, hit the accelerator, please. Okay? So when somebody hits the accelerator, they go faster, right? Okay, their speed increases. So acceleration is just a change in velocity, not a change necessarily, doesn't have to be a change in speed, but it's a change in velocity. And since velocity has both speed and direction, okay, we say that somebody is accelerating if they're changing their speed or if they're changing their direction. So in this case, we have a car going straight. It's going from a velocity of 10 kilometers per hour to 20 kilometers per hour. It's accelerating, right? What we call deceleration is also acceleration, okay? So in this case, it's got negative acceleration. The car is going from 30 to 0, okay? So it's decelerating. It will have negative acceleration. In this case, a car, let's just say it's going at constant speed. Let's say it's going at 30 miles per hour in a circle. 30 miles per hour. It's not changing its speed, but it's changing its direction. At any given point on there, we would say the direction of the car looks like this. Here, the car looks like, here the car looks like this. If the car was right here, its direction is like this. If the car is over here, here's my square car, its direction, we say, is kind of a line tangent to its motion. Okay, so it's really changing its direction. It could be going at constant speed, but we would call that acceleration. It is acceleration. So we calculate acceleration. We're just sticking with average. By the way, you're probably good with this. In statistics, I guess it would be statistics, anytime you see a bar, you see where this is a bar, okay? Anytime you see a bar over anything, that means average. So what we do is we take the final, okay, so little subscript f means final, okay? The final velocity, and from that we subtract the initial velocity. So it's always final minus initial. Final velocity minus initial velocity divided by the time over which that change in velocity occurred. Another thing I'd like to introduce is this idea that we have a lot of changes in. So change in velocity is acceleration. We get tired of writing the word change in, so we actually use the Greek letter delta. Anytime you see this triangle, that triangle is the Greek letter delta, and it means change in. Okay? So we're going to be kind of using that. Delta, the triangle means change in. So the way you would read this is change in velocity, okay, divided by change in time. Change in velocity divided by change in time. And by the way, anytime you see the delta, the change in, it's always final minus initial. It is always final minus initial. And that kind of throws students off sometimes. Throws me off sometimes. That delta change in, it's always final, just like we did final velocity minus initial. All right, so let's do a problem. No problem. Okay, so a car travels due north. So we got direction, so it must be a velocity. So it travels due north from rest. So actually, we might want to go ahead and doodle this. Okay, so it's traveling due north. Here's my car. I'll just go ahead and make it a square, rectangle. Here's my car traveling due north, okay, from rest. So actually, what I'm going to do here is I'm going to say v sub I, that's initial velocity, is equal to 0. Does that make sense? Because it's traveling from rest. Okay. I'm going to go ahead and draw another car up here. Maybe I need a bigger diagram. There's my other car up here. And I'm going to go ahead and say in 3.4 seconds, now it's traveling at 15 meters per second. So over here, next to my upper triangle, I'm going to put v sub f is equal to 15 meters per second. I guess I should put v sub I, my initial velocity, is 0 meters per second. Cool, and that's it. What is the acceleration over that time interval? So we could go ahead and doodle. We could say average acceleration, a bar, is equal to delta v. Doesn't sound so scientific. Delta v, change in velocity, divided by change in time. Okay, so delta v, that's final minus initial. So it looks to me like it's 15 meters per second minus 0 meters per second divided by 3.4 seconds. Does that seem right? I'm liking it. So we're gonna, this one's not too bad. We're gonna go with 2 digits, right, when we write it down. So 15 divided by 3.4. 2 digits, I got 4.4. Is that what you guys got? Now here's the deal. You're like, well, what will the units be? Well, we have to keep the units that were in our problem. So when you work problems like you did, you just need to make sure you have your units. So actually, units of acceleration are meters per second per second. Meters per second per second. Sometimes, and we get rolling here on Wednesday, that actually boils down to meters per second squared. That's what units of acceleration are. And that's your answer. Okay. Another one. This one, we can go ahead and draw a similar picture, but this time it's traveling due west. Okay, and notice in this case, okay, The initial velocity, v sub I, is equal to 29 meters per second. Okay, and the car comes to a full stop, so v sub f is equal to 0 meters per second. And the time over which it occurs, t, is equal to 10.2 seconds. So, using the equation we had over at the previous slide, acceleration, average acceleration, is equal to delta v divided by delta t. Okay, and delta v is final velocity minus initial velocity. So in this case, our final velocity is 0, isn't it, meters per second. Our initial velocity is that minus 29 meters per second, okay, divided by delta t, and that's our 10.2 seconds. So in this case, it kind of, when you do the math, you're going to come up with a negative 29 in the top, aren't you? So negative 29 divided by 10.2. And then how do we need to round this one? How many digits? What do you think? Just 2, right? Okay, so I got negative 2.8. Is that what y'all got? Negative 2.8. And again, units are meters per second per second. Negative 2.8 meters per second, or negative 2.8 meters per second squared. Acceleration. Any questions about that? Cool. So I picked out, I hope they're directly related, related problems on 49 and page 50, and these are available in WebAssign now too. And they're very similar problems in WebAssign, the online thing, maybe just different numbers. So problems 12 and 14, and if you're looking for help, problems 11 and 13 are very similar to these. So yeah, it's all good. Now remember kind of the way, we don't have a whole lot more to do. We're going to talk about Newton's laws of motion when we come back on Wednesday. And then we're going to go on to another little piece of physics. So, okay. Yay! Let me know if you have any questions. That's it.